Newcastle Quayside, 1875. The gleaming brass fittings of Armstrong's revolutionary hydraulic crane caught the morning light as it stood beside its ancient rival, a 40-year-old manual crane operated by six dock workers using nothing but rope, pulleys, and raw muscle. The hydraulic marvel could lift 5 tons in 30 seconds using 600 psi water pressure. The old crane took 8 minutes for the same load. For 30 years, Armstrong's hydraulic technology had been the envy of the industrial world, installed at ports from Liverpool to Hamburg. But this morning, something was terribly wrong. Hydraulic fluid pooled beneath the modern machine's precision-engineered base while the manual crane kept working, steady as clockwork. European engineers had proclaimed hydraulic systems the future of cargo handling. Manual cranes were relics of a primitive past. Yet here stood undeniable proof that the most advanced engineering might not always mean the most reliable engineering. The question that would reshape industrial thinking was beginning to surface. What happens when technological complexity becomes the enemy of dependability? The revelation began 30 years earlier, when William Armstrong stood knee-deep in the River Dee, fishing rod forgotten in his hands as he watched a water wheel turn lazily beside the mill. The lawyer's methodical mind couldn't ignore what he was seeing, thousands of gallons rushing past unused while the wheel captured perhaps 1/10 of the river's power. Armstrong had built his Newcastle practice on precision, analyzing property disputes and commercial contracts with the same systematic approach he now applied to this waste of natural energy. That evening, in his Jesmond study, he filled 3 pages with calculations, sketching how the city's new water pressure system from Whittledean Reservoir could harness 400 feet of head pressure for industrial purposes. By 1846, Armstrong had transformed his insight into Newcastle's first hydraulic crane. The installation on the quayside drew crowds of skeptical dock workers and curious engineers who had never seen cargo lifted by water pressure alone. The numbers spoke louder than any demonstration. 5 tons hoisted in 30 seconds, compared to the 8 minutes required by manual crews operating the traditional rope and pulley systems. The Newcastle Corporation, impressed by the efficiency gains, commissioned 3 additional cranes before the year ended. Armstrong's small engineering firm suddenly found itself inundated with orders from ports across Britain. The growth was methodical and relentless. By 1850, the Elswick Works produced 45 cranes annually, employing 200 skilled craftsmen who had mastered the precision tolerances required for high-pressure hydraulic systems. The operation expanded to 75 cranes per year by 1852, settling into steady production of 100 units. Annually, a pace that continued for decades. Each crane represented a marvel of engineering sophistication, with brass fittings machined to thousandths of an inch, leather gaskets treated with specialized compounds, and cylinder walls polished to mirror smoothness. The technology's reputation spread across Europe. Hamburg's harbor master requested detailed specifications. Rotterdam's port authority sent engineers to study the Newcastle installations. By 1860, Armstrong hydraulic cranes operated at every major British port and dozens of continental facilities. The system seemed to have achieved mechanical perfection, consistent power delivery, precise load control, and lifting capacity that dwarfed traditional methods. But by 1875, whispered doubts began circulating among dock workers and port engineers. The problem started small, minor seal weepage that required monthly attention, occasional pressure drops during peak operation periods, and the need for specialized maintenance that local craftsmen couldn't perform. European engineers visiting from Hamburg and Rotterdam, initially impressed by the hydraulic system's capabilities, began noting troubling patterns. Hydraulic seals failed predictably after 5 to 7 years of operation, requiring complete system rebuilds. Water contamination from Newcastle's industrial district caused pressure inconsistencies that affected lifting precision. Most concerning, the cranes required specialized technicians for repairs, creating dependence on Armstrong's service network. The manual cranes, meanwhile, continued their steady work with almost boring reliability. Some had operated for 40 years with nothing more than annual rope replacement and monthly bearing lubrication. Dock foreman Thomas Mackenzie, who had supervised cargo operations since the 1850s, began documenting the stark differences. His weathered logbooks showed manual cranes achieving 97% uptime over decades of service. The hydraulic systems, despite their impressive capabilities, averaged 80% availability when accounting for maintenance schedules and unexpected failures. The crisis arrived on a gray November morning in 1875. Armstrong's newest hydraulic crane, installed just 6 months earlier with improved sealing technology, suffered a catastrophic failure while lifting 200 tons of Welsh coal destined for a London steamer. The massive load hung suspended 40 feet above the dock as hydraulic fluid sprayed from ruptured seals, creating a dangerous emergency that required manual intervention by 3 backup cranes to safely lower the cargo. Harbor Master William Clayton found himself confronting an uncomfortable mathematical reality. The incident report spread across his desk told a story that contradicted 30 years of hydraulic success. While Armstrong's cranes could indeed lift 5 tons in 30 seconds, achieving theoretical productivity of 600 tons per hour, their actual performance was compromised by maintenance requirements, seasonal weather effects on hydraulic fluid, and the specialized knowledge needed for repairs. The manual cranes, upgraded over decades with steel cables and improved pulleys, required 8 minutes per 5-ton lift, but operated consistently regardless of weather, contamination, or mechanical wear. Clayton's analysis revealed the hidden economics of complexity. A hydraulic crane's initial cost of £800 seemed reasonable compared to a manual crane's £400 price tag when factoring the speed advantage. But operational costs told a different story. Hydraulic systems required seal replacement every 6 to 8 months at £15 per service, quarterly inspections by specialized technicians, and annual pressure vessel certification. Over 30 years, a hydraulic crane's total cost reached £1,200. A manual crane requiring only rope replacement every 18 months and basic maintenance cost £600 over the same period. The dock workers had noticed what the engineers were reluctant to admit. Mackenzie's crews trusted the manual cranes implicitly, knowing they could diagnose problems through sound and vibration, repair most issues with common tools, and maintain consistent performance through careful daily operation. The hydraulic systems, despite their impressive engineering, remained mysterious black boxes that only specialists could properly service. When they worked perfectly, they were magnificent. When they failed completely and expensively. As winter approached, the fundamental question could no longer be avoided. Had technological sophistication created more problems than it solved? The answer would reshape how engineers thought about industrial progress, reliability, and the true meaning of mechanical advancement. Robert Whitworth arrived at the Elswick Works before dawn, his leather satchel heavy with pressure gauges, calipers, and sample containers filled with failed hydraulic components. Armstrong's chief hydraulic designer had spent the previous 3 months systematically analyzing every seal failure, cataloging the precise conditions that led to system breakdowns. The challenge was immense. Containing 600 psi water pressure with 1870s technology meant relying on leather gaskets cut from specially treated cowhide, hemp packing soaked in tallow and linseed oil, and experimental rubber compounds that degraded unpredictably under temperature cycling. Whitworth's workshop had become a laboratory of failure analysis. Dozens of ruptured seals lined wooden shelves, each tagged with installation date, operational hours, and failure mode. The patterns were troubling but consistent. Leather gaskets hardened and cracked after 6 months of winter operation, when cold water caused repeated thermal contraction. Hemp packing, while initially effective, absorbed contaminants from Newcastle's increasingly polluted water supply, causing gradual swelling that compromised seal integrity. The early rubber compounds, imported at considerable expense from American suppliers, proved susceptible to the mineral deposits that accumulated in the city's pressure system. The mathematics of maintenance painted a stark picture. Data collected from 37 operational cranes across British ports revealed that hydraulic systems required seal replacement every 6 to 8 months, costing £15 per crane, equivalent to £900 in modern currency. Manual cranes needed new rope annually at £3 and bearing grease monthly at 6p. Over a 30-year operational life, a hydraulic crane's maintenance costs reached £450. A manual crane required £120 for the same period. The hydraulic speed advantage, lifting loads 5 times faster than manual systems, was offset by reliability concerns that no amount of engineering refinement seemed capable of addressing. Whitworth attacked the sealing problem with methodical precision, drawing on his background in millwright mechanics and his father's experience with high-pressure steam systems. He redesigned gasket profiles to distribute pressure more evenly, experimented with brass compression fittings that maintained consistent force regardless of temperature changes, and developed improved rubber compounds using sulfur vulcanization techniques. His most ambitious project involved precision machined cylinder walls polished to mirror smoothness, reducing friction that contributed to seal wear. The breakthrough came in 1877 with Whitworth's hydraulic accumulator system. The 300-foot tower, constructed of wrought iron plates riveted with steam-powered precision, maintained consistent pressure by storing hydraulic energy in massive elevated tanks. The system compensated for demand fluctuations that had previously stressed seals during peak loading periods. Similar towers rose at Grimsby and Liverpool, their imposing silhouettes becoming symbols of British hydraulic engineering leadership. For 2 years, the improvements showed promise. Failure rates dropped from 60% annually to 30% as Whitworth's enhanced sealing systems proved more durable than earlier designs. The Elswick Works expanded to accommodate growing international demand, employing 3,800 workers who produced not only hydraulic cranes, but also the precision artillery that was making Armstrong's reputation worldwide. Orders arrived from Hamburg, Rotterdam, and St. Petersburg, where harbor authorities were eager to modernize their cargo handling capabilities. But the fundamental challenge remained unsolved. While Whitworth's innovations extended hydraulic system life, they also increased complexity and manufacturing costs. Each crane now required 17 different seal types, machined to tolerances that pushed the limits of available manufacturing equipment. Installation demanded specialized knowledge that local port authorities rarely possessed. Most critically, the system still depended on water quality that varied significantly between locations and seasons. Thomas Mackenzie's observations from the Newcastle quayside provided sobering counterpoint to the engineering optimism. The dock foreman had begun documenting how manual crane operators developed techniques that actually improved performance over time. Experienced crews learned to coordinate their movements with mechanical precision, achieving lifting rates that approached theoretical limits while maintaining the systems through intuitive understanding of rope tension, pulley alignment, and load distribution. The manual cranes, rather than degrading with age, often perform better after years of operation as mechanical tolerances settled and operators refined their methods. The economic analysis grew more complex as European competitors responded to British hydraulic dominance. German engineers, led by Hamburg's systematic harbor modernization program, developed enhanced manual systems that challenged hydraulic advantages. Compound pulley arrangements achieved 50-to-1 mechanical advantage ratios, steel cables replaced traditional hemp rope, and precision bearings manufactured in Stuttgart reduced friction losses. These improved manual cranes could lift 3 tons efficiently, matching hydraulic systems' practical capacity for most cargo operations while maintaining the mechanical simplicity that had proven so reliable. Whitworth found himself caught between engineering perfectionism and operational reality. His technical notebooks filled with increasingly sophisticated solutions, multiple backup sealing systems, automated pressure regulation, remote monitoring capabilities that addressed hydraulic reliability concerns while adding layers of complexity that manual systems avoided entirely. Each innovation solved specific problems while creating new dependencies that required additional expertise to maintain. The accumulator towers stood as monuments to hydraulic engineering achievement, their massive presence dominating port skylines across Britain, but their operational records told a sobering story. While they successfully maintained pressure consistency, they required quarterly inspection, annual structural certification, and specialized maintenance that cost more than entire manual crane installations. The towers worked magnificently when properly maintained, but their failure could disable entire port operations, a vulnerability that manual systems distributed across individual cranes never created. By 1879, Whitworth's engineering triumph was becoming an operational burden that would soon face its ultimate test against the reliability that only mechanical simplicity could provide. By 1878, Armstrong's hydraulic cranes had achieved international dominance that seemed unshakable. Liverpool docks operated 16 units that handled the majority of transatlantic cargo, their brass fittings gleaming in the industrial haze as they lifted cotton bales and machinery with mechanical precision. London's Thames facilities had installed 12 cranes along the commercial wharves, where they managed the enormous volume of goods flowing through the empire's commercial heart. From Hamburg to St. Petersburg, European ports relied on British hydraulic technology that had revolutionized cargo handling across the continent. The Elswick Works had become a manufacturing marvel, employing 3,800 workers across sprawling workshops where precision machinery produced both hydraulic cranes and the military artillery that was establishing Armstrong's reputation as Britain's premier armaments manufacturer. The company's success seemed to validate the fundamental principle of industrial progress, that sophisticated engineering could solve any operational challenge through systematic application of scientific principles. Visitors from American ports, European industrial centers, and colonial administrations toured the facilities, studying the manufacturing processes that produced these mechanical marvels. But troubling patterns were emerging in operational reports from established installations. Port managers from Liverpool, Hamburg, and London documented a consistent phenomenon. Hydraulic systems performed magnificently for 3 to 5 years. Then maintenance costs began escalating rapidly. Internal leakage increased as seals aged beyond their design limits. Precision tolerances degraded as repeated pressure cycles stressed mechanical components, and replacement parts became critical bottlenecks that could disable operations for weeks while specialized components were manufactured and shipped. The reliability paradox became most apparent when comparing operational data across different crane types. Manual cranes, conversely, improved with age as operators developed sophisticated techniques and mechanical systems settled into optimal tolerances. Experienced dock crews could achieve lifting rates that approached theoretical efficiency limits while performing intuitive maintenance based on decades of accumulated knowledge. The manual systems became extensions of human expertise rather than replacements for it. Johann Richter's analysis from Hamburg provided the most systematic comparison of competing technologies. The Prussian-trained harbor master had maintained detailed performance records for 5 years, documenting both British hydraulic systems and enhanced German manual cranes operating side by side on the same docks. His data revealed uncomfortable truths that challenged the assumed superiority of hydraulic technology. While Armstrong's cranes achieved 15 tons per hour when operating perfectly, they experienced downtime averaging 20% annually due to maintenance requirements, seal failures, and specialized repair procedures. The German manual systems, upgraded with compound pulley arrangements and precision steel cables, achieved 8 tons per hour consistently with downtime below 3% annually. When adjusted for reliability, the effective throughput comparison was startling. Hydraulic cranes delivered 12 tons per hour average performance. Manual systems 7.8 tons per hour. The hydraulic advantage, while still significant at 54%, was far below the theoretical 88% that had justified the technology's adoption. Richter's winter operations data proved even more revealing. Hamburg's harsh seasonal conditions exposed fundamental vulnerabilities in hydraulic systems that manual cranes avoided entirely. Cold temperatures caused hydraulic fluid viscosity changes that reduced lifting speed and increased pressure requirements. Seal brittleness in freezing conditions led to catastrophic failures that could disable cranes for weeks. Water contamination from ice formation created pressure irregularities that affected load control precision. The manual cranes, operating through mechanical principles that remained consistent regardless of temperature, maintained steady performance throughout Hamburg's brutal winters. Steel cables proved more durable than hydraulic seals in extreme weather. Pulleys required only periodic lubrication with common grease, and repairs could be completed by local craftsmen using standard tools. The reliability advantage became most critical during peak shipping seasons when equipment failure created expensive delays. Armstrong's engineering team, led by Robert Whitworth, responded to the emerging challenges with characteristic precision and determination. They developed cold weather hydraulic fluids that maintained consistent viscosity across temperature ranges, designed improved seal compounds that resisted freeze-thaw cycling, and created modular replacement systems that reduced repair downtime. Each innovation addressed specific operational problems while adding complexity that manual systems avoided through mechanical simplicity. The international competition intensified as German manufacturers introduced systematic improvements to manual crane technology. Stuttgart's precision bearing industry produced components that reduced friction losses to levels approaching hydraulic efficiency. Krupp Steel Works developed cable systems with strength-to-weight ratios that enabled compound pulley arrangements achieving 60-to-1 mechanical advantage. These enhanced manual systems could lift 3 tons efficiently while maintaining the operational simplicity that had proven so reliable across decades of service. The economic implications became increasingly difficult to ignore. Harbormaster William Clayton's detailed cost analysis for Newcastle's operations revealed that hydraulic systems required specialized maintenance infrastructure that manual cranes avoided entirely. Each hydraulic installation needed quarterly inspection by certified technicians, annual pressure vessel testing, and access to precision replacement parts manufactured exclusively at Elswick. Manual cranes required rope replacement by local riggers, bearing lubrication with common industrial grease, and repairs using tools available in any port workshop. The reliability gap was widening despite continuous engineering improvements. While Whitworth's innovations extended hydraulic system life and improved performance, they also created dependencies that manual systems never required. Hydraulic cranes needed consistent water pressure, specialized maintenance knowledge, and replacement parts manufactured to precise tolerances. Manual cranes operated effectively with basic mechanical principles that remained unchanged regardless of location, season, or operator skill level. The fundamental question that had been lurking beneath 30 years of hydraulic success was becoming impossible to avoid. Had engineering sophistication created a technology that worked magnificently under ideal conditions, while proving vulnerable to the unpredictable realities of industrial operations? The answer would soon be tested under conditions that would expose the true cost of complexity versus the enduring value of mechanical simplicity. Winter 1881 brought the crisis that exposed every vulnerability in Armstrong's hydraulic empire. The season arrived with brutal cold that froze the River Tyne and coated Newcastle's industrial district in ice that persisted for weeks. Temperatures dropped to levels that transformed hydraulic fluid into thick, viscous liquid that moved sluggishly through precision-machined cylinders designed for free-flowing operation. The specialized seals that Robert Whitworth had perfected over years of engineering refinement became brittle in the extreme cold, losing the flexibility essential for containing 600 psi water pressure. The cascade of failures began on a January morning when the largest hydraulic crane at Newcastle's central dock seized during a routine lift, its cylinder packed with hydraulic fluid too thick to flow properly. Within hours, 2 additional cranes suffered catastrophic seal ruptures as frozen gaskets cracked under pressure, spraying hydraulic fluid across the dock and creating hazardous conditions that halted cargo operations. The simultaneous failure of 3 cranes during peak shipping season created an operational emergency that tested every assumption about technological reliability. Thomas Mackenzie found himself managing a crisis that validated his deepest concerns about complex technology. The manual cranes, unaffected by temperature extremes that crippled their hydraulic counterparts, suddenly became the dock's salvation. His crews worked around the clock to handle overflow cargo using equipment that many had dismissed as obsolete. The irony was not lost on Mackenzie. 40-year-old manual cranes were keeping Newcastle's port operational, while Armstrong's engineering marvels sat disabled, awaiting specialized repair that could take weeks to complete. The economic reckoning arrived with mathematical precision that harbor authorities could no longer ignore. William Clayton's emergency assessment revealed the true cost of technological dependence during critical failures. Each disabled hydraulic crane represented not only lost lifting capacity, but also the specialized maintenance infrastructure required for repair. Replacement seals had to be manufactured at Elswick to exact specifications. Certified hydraulic technicians were scarce during winter months, and pressure testing equipment needed for safe restart was available only from Armstrong's service network. The manual cranes, meanwhile, required nothing more than basic maintenance that dock workers performed with tools available in any port workshop. Steel cables remained flexible in freezing temperatures. Pulleys operated smoothly with periodic lubrication, and mechanical systems that had functioned reliably for decades continued working regardless of weather conditions. The reliability gap that had been slowly widening over years of operation became a chasm during the winter crisis. Clayton's detailed analysis of the disaster provided sobering insights into the hidden vulnerabilities of sophisticated technology. The hydraulic cranes, when operational, achieved theoretical lifting rates of 15 tons per hour that exceeded manual systems by significant margins. But their susceptibility to environmental conditions, dependence on specialized maintenance, and catastrophic failure modes created operational risks that manual systems avoided through mechanical simplicity. The financial implications were staggering. Each hydraulic crane failure during peak shipping season cost an estimated £200 in lost productivity, emergency repairs, and cargo delays. The 3 simultaneous failures represented £600 in immediate losses, with additional costs mounting daily until repairs could be completed. Manual crane operations, while slower, provided consistent throughput that enabled port operations to continue despite reduced capacity. Johann Richter arrived from Hamburg in February to assess the Newcastle situation, bringing operational data from German ports that had experienced similar winter challenges. His report delivered devastating conclusions about hydraulic technology's fundamental limitations. Hamburg's installations had suffered comparable failures during cold weather, requiring extensive winterization measures that added significant operational costs. The German manual systems, enhanced with precision bearings and compound pulley arrangements, had maintained steady operations throughout the harsh winter. Richter's assessment was methodical and unsparing. British hydraulic cranes represented engineering excellence that worked perfectly under ideal conditions but proved vulnerable to real-world operational challenges. Temperature extremes, water quality variations, and maintenance requirements created dependencies that manual systems avoided entirely. The German approach of enhancing proven mechanical principles rather than replacing them with complex alternatives was proving more operationally sound than the British pursuit of technological revolution. The international implications extended beyond Newcastle's docks. Port authorities across Europe were reassessing hydraulic installations that had seemed so promising during favorable conditions. Reports from St. Petersburg described similar winter failures, while Mediterranean ports noted problems with hydraulic fluid contamination from salt air. The technology that had revolutionized cargo handling was revealing systematic vulnerabilities that threatened operational reliability. Armstrong's response to the crisis demonstrated both the company's engineering capability and the limitations of complexity-based solutions. Whitworth's team developed winterized hydraulic fluids, cold weather sealing systems, and heated cylinder arrangements that addressed temperature-related failures. But each solution added components, maintenance requirements, and potential failure points that manual systems avoided through mechanical simplicity. The enhanced manual systems being developed in Germany offered a different approach that combined reliability with improved performance. Compound pulley arrangements using precision steel cables achieved mechanical advantages approaching hydraulic systems while maintaining the operational simplicity that had proven so durable. These systems could be repaired by local craftsmen, operated effectively in any weather, and upgraded gradually without requiring complete replacement of existing infrastructure. The winter of 1881 had exposed the fundamental tension between engineering sophistication and operational reliability that would reshape industrial thinking about technological progress. The crisis proved that advanced engineering solutions must account not only for ideal performance, but also for the unpredictable challenges of real-world operations, where environmental conditions, maintenance limitations, and human factors determined practical success. As spring arrived and the damaged hydraulic cranes were gradually restored to service, the uncomfortable questions raised by the winter failures could no longer be avoided. The path forward would require choosing between the pursuit of engineering excellence and the practical demands of dependable operations that kept industrial civilization functioning day after day. By 1885, the verdict had crystallized into operational reality that port authorities across Britain acknowledged without fanfare or official proclamation. New Dock. Construction at Newcastle, Liverpool, and London specified hybrid systems that balance technological capability with operational reliability. Hydraulic cranes were designated for maximum capacity loads exceeding 8 tons, where their superior lifting power justified the complexity and maintenance requirements. Manual systems, upgraded with steel cables and precision bearings, handled the 80% of cargo operations that required consistent daily performance rather than exceptional capability. The quiet victory belonged to neither technology exclusively, but to the practical wisdom that recognized each system's appropriate role. Thomas Mackenzie's crews had developed operational procedures that maximized the strengths of both approaches, using hydraulic cranes for heavy lifts during favorable conditions while relying on manual systems for routine operations and emergency backup. The dock foreman's logbooks documented a fundamental shift in thinking about industrial progress, where technological advancement meant choosing the right tool for specific purposes rather than pursuing universal solutions. William Armstrong's hydraulic revolution had achieved its intended purpose while inadvertently proving limitations that no amount of engineering refinement could overcome. His cranes demonstrated unprecedented capability when conditions were optimal, maintenance was consistent, and specialized expertise was available. But they required infrastructure support, precision manufacturing, expert technicians, reliable supply chains that manual systems avoided through mechanical simplicity rooted in centuries of proven mechanical principles. The operational data told a complete story with mathematical precision that eliminated sentiment from technological assessment. After 40 years of service, the original 1845 manual cranes on Newcastle Quayside continued lifting cargo daily with maintenance requirements unchanged since installation, rope replacement every 18 months, bearing lubrication monthly, and occasional pulley adjustment by local craftsmen. Their cumulative operational cost remained predictable and minimal, requiring no specialized knowledge or precision components manufactured to exacting tolerances. Armstrong's hydraulic installations presented a contrasting narrative of technological sophistication paired with operational complexity. Of the original systems installed during the 1850s, only 2 remained in service, extensively rebuilt with modern components that addressed earlier design limitations while introducing new maintenance requirements. The surviving cranes required quarterly seal inspection by certified technicians, annual cylinder rebuilding with precision machined parts, and continuous monitoring by specialists trained in hydraulic system operation. The economic analysis had evolved beyond simple cost comparisons to encompass the broader implications of technological dependence. Manual. Cranes created no external dependencies. They operated effectively with materials and expertise available in any industrial port, required no specialized supply chains, and could be maintained by workers trained through traditional apprenticeship methods. Hydraulic systems, despite their impressive capabilities, created networks of dependence that extended from Elswick's manufacturing facilities to specialized service organizations that few ports could maintain independently. The international perspective provided the clearest validation of operational reality over engineering theory. American dock engineers arrived in Newcastle during 1888, representing port authorities from New York, Boston, and Philadelphia who were planning major infrastructure expansions. They studied both systems with systematic thoroughness, documenting performance capabilities alongside maintenance requirements, operational costs, and reliability data across different seasonal conditions. The American analysis reached conclusions that would influence industrial development across the Atlantic. Rather than choosing between hydraulic sophistication and mechanical simplicity, they identified a third approach that combined proven reliability with enhanced power. Steam-powered mechanical cranes could deliver lifting capacity approaching hydraulic systems while maintaining the operational characteristics that made manual cranes so dependable. Steam technology, already mastered in American factories and railroads, offered familiar maintenance procedures and readily available expertise. The American solution represented evolutionary, rather than revolutionary thinking about technological progress. Instead of replacing proven mechanical principles with complex alternatives, They enhanced existing systems with additional power sources that maintained operational simplicity. Steam powered mechanical cranes could be repaired by railroad mechanics, operated by workers trained on familiar equipment, and maintained with standard industrial supplies available throughout the expanding American transportation network. Robert Whitworth's final assessment of the hydraulic program demonstrated the intellectual honesty that characterized the best engineering thinking. His technical reports acknowledged that hydraulic systems had achieved their design objectives: unprecedented lifting speed, precise load control, and mechanical capabilities that exceeded traditional methods. But they had also revealed the hidden costs of complexity that manual systems avoided through operational simplicity. The lasting insight transcended the specific comparison between hydraulic and manual cranes to address fundamental questions about technological progress. Advanced engineering solutions must account for more than performance capabilities under ideal conditions. They must function reliably within the practical constraints of real-world operations where environmental challenges, maintenance limitations, and human factors determined success or failure. Harbor Master William Clayton's final operational summary provided the institutional perspective that balanced engineering achievement with practical requirements. The hydraulic cranes had revolutionized cargo handling capabilities, enabling port operations that would have been impossible with manual systems alone. But the manual cranes had provided the operational foundation that kept commerce flowing consistently regardless of weather, maintenance schedules, or technical complications. The Newcastle quayside stood as a testament to both approaches: hydraulic cranes handling exceptional loads with mechanical precision, while manual cranes maintained steady operations that formed the backbone of daily commerce. The lesson was not that one technology was superior to another, but that engineering excellence sometimes required knowing when complexity served genuine needs and when simplicity provided more reliable solutions. Armstrong's hydraulic revolution had succeeded by proving that natural forces could be harnessed through precision engineering to amplify human capability exponentially. The manual cranes had succeeded by proving that mechanical principles, refined through centuries of practical application, could provide dependable service that withstood the test of time, weather, and operational reality. Both lessons would guide the industrial age toward a more nuanced understanding of technological progress that valued reliability alongside capability,